we stand on the surface of a world that hums with a history so vast, so profound, it dwarfs our every conception of time. Beneath our feet, a silent testament to epochs long past is etched into the very bedrock. These are not mere stones, but pages of a colossal book, each layer a chapter, each fossil a word, whispering tales of a planet forged not in moments, but in eons. We perceive time through the rhythm of our own fleeting lives, a heartbeat against the slow, inexorable pulse of geological ages. The mountains we see, seemingly eternal, have risen and crumbled countless times. The oceans, vast and deep, have ebbed and flowed across continents, carving canyons and nurturing life that now exists only as spectral imprints in the stone. And real quick, make sure to subscribe and hit the notification bell for more videos. Now let's keep going. This is the realm of deep time, a domain where the familiar scales of human experience dissolve. It is a forgotten language, written in rock and dust, a narrative of cosmic coincidences and biological marvels. To listen requires a shift in perspective, a willingness to surrender to the immense patience of the earth itself. We will journey through these buried chronicles, not as observers, but as seekers. We will trace the slow dance of continents, the fiery birth and silent death of stars, and the improbable emergence of life from primordial soup. Each revelation will be a carefully placed stone, building a bridge to understanding a planet that has lived and evolved long before us, and will continue long after. But before we can truly hear the whispers of the strata, we must first understand the language they speak. We must learn to read the signs left behind by cataclysm and calm, by the crushing weight of ice and the searing breath of volcanoes. This is not a lesson. It is an awakening to the profound saga unfolding beneath our very feet. To begin this journey, we must first confront the most fundamental question of all. How do we even know the age of things so ancient? We will delve into the very foundations of our understanding, exploring the ingenious methods that allow us to date the immeasurable. And in doing so, we will begin to unravel the oldest secrets of our world. Our perception of time is a fragile thing, bound by the flicker of a candle and the arc of a day. Yet the earth holds within its core an unseen clockwork, a mechanism far older than any human invention, one that has meticulously recorded the passage of billions of years. To unlock its secrets, we turn to the very elements that compose our world. Radioactive isotopes, these tiny, unstable hearts of atoms, are the true chronometers of our planet. They decay at a predictable, unyielding rate, a process as inevitable as the setting sun. It is this steady, unwavering exodus of energy that allows us to rewind the tape of time, to peer back into the primordial mists. Consider uranium, a metal of immense density. It does not remain uranium forever. Over vast stretches of time, It transmutes, shedding particles, transforming into lead. This transmutation is not random. It follows a precise schedule. A half-life, the time it takes for half of a sample to decay. With a sample of uranium in hand, and knowing its half-life, we can measure the ratio of uranium to lead and deduce the age of the rock. This is not magic, but fundamental physics, applied with the patience of the earth itself. We find these natural clocks ticking in the oldest rocks, in the very meteorites that fell to Earth in its infancy, offering us a glimpse into the solar system at its dawn. We analyze zircons, tiny crystals that trap these isotopes within their structure, becoming time capsules of unimaginable antiquity. Each measurement is a carefully calibrated step backward, a confirmation of the Earth's staggering age. We are not guessing. We are reading a ledger that has been kept since the planet's very formation. But this clockwork is not always straightforward. Layers can be disturbed. Rocks can be melted and reformed, obscuring the pristine record. This steady decay is the bedrock of our understanding, the foundational principle that allows us to construct the grand timeline of Earth's history. Yet this clockwork is not the only story the rocks tell. They are also a record of profound, earth-shattering events. And to understand these events, we must first look to the very building blocks of our planet and the unimaginable forces that shaped them. The story of these transformations is deeply intertwined with the early formation of our solar system, leading us to the fiery birth that shaped everything we see. Before there were oceans, before there were continents, before there was even a stable crust, there was fire. Our planet, in its nascent stages, was a molten inferno, a raging ball of liquid rock and incandescent metal. This was the primordial forge, a violent crucible where Earth was born from the swirling dust and gas of the early solar nebula. Imagine a vast cosmic cloud, a stellar nursery ignited by the birth of a star, our sun. Around this young star, a disk of debris began to coalesce, clumping together under the relentless pull of gravity. These clumps grew, colliding and merging, each impact adding more mass, more heat. The early Earth was a planet in constant creation, a relentless bombardment of planetesimals. The energy from these impacts was immense, sufficient to melt the accumulating matter, keeping the young Earth in a state of perpetual flux. It was a surface of liquid rock, a sea of magma, devoid of the familiar solidity we know today. Within this molten heart, the processes that would define our planet began their slow work. Heavy elements, like iron and nickel, sank towards the center, driven by density, forming the molten core. Lighter elements, silicates, and volcanic gases rose to the surface, creating a primitive mantle. This differentiation was a crucial step, establishing the internal structure that would ultimately allow for plate tectonics and the very existence of land and sea. The atmosphere of this early Earth was a toxic brew, dominated by volcanic gases like carbon dioxide and water vapor, with little to no free oxygen. It was a far cry from the life-sustaining envelope we breathe today. The surface, continually churned by volcanic activity and asteroid impacts, offered no respite, no stable ground. This fiery genesis was not unique to Earth. It was a common fate for the rocky planets forming in the inner solar system. But it was during this violent infancy that the fundamental forces that would shape Earth's future were set in motion. The heat from this formation and the ongoing radioactive decay within its core created the engine that drives geological change. Understanding this fiery genesis is essential, for it laid the groundwork for everything that followed. It created the planet itself and the internal heat that would eventually power its most dramatic transformations. But this molten world was not static. A profound shift was on the horizon, a colossal event that would forever change the face of our planet and initiate the long, slow awakening of life. We now turn to the immeasurable power of the Great Impact. The early solar system was a chaotic place, a celestial demolition derby where celestial bodies were in constant, violent motion. Among the most significant of these collisions, the one that fundamentally reshaped our planet and set the stage for its future, was the colossal impact that gave birth to our moon. Imagine a rogue planetoid, a world-sized object, hurtling through the nascent solar system. Scientists call this hypothetical body Theia. It was roughly the size of Mars, a formidable presence on a collision course with the proto-Earth. The impact was not a glancing blow. It was a cataclysmic, planet-shattering event. The sheer force of this collision vaporized vast portions of both Theia and Earth, sending a stupendous plume of molten rock and debris into orbit. This ejected material, swirling in a rapidly expanding ring around our battered planet, began to coalesce under its own gravity. Over time, as the debris settled and condensed, it formed our moon. This was not a gentle birth. The young Earth would have been a scene of unimaginable devastation. For a time, it may have been a ring of fire, a planet surrounded by its own incandescent offspring. The molten surface would have been further churned, its early differentiation disrupted. The heat generated by the impact would have been catastrophic, likely remelting much of the planet's surface. This event, occurring perhaps around 4.5 billion years ago, had profound consequences. It not only created our moon, which would later play a crucial role in stabilizing Earth's tilt and driving tides, but it also significantly altered Earth's composition and momentum. Some theories suggest this impact may have even tilted Earth's axis, contributing to the seasons. The debris from this impact would have rained back down on Earth for millennia. A constant barrage of molten fragments. The young atmosphere would have been thick with vaporized rock and gases, creating a searing greenhouse effect. The surface, once again, was a molten sea. Yet, within this destruction lay the seeds of future stability. The formation of the moon, though violent, introduced a gravitational anchor that would eventually help regulate Earth's rotation and orbit. And as the planet slowly cooled from this cataclysm, the stage was set for the next critical phase: the arrival of water, the lifeblood of our world. The sheer energy released by this impact also had a curious side effect, a subtle but persistent change that began to reshape the very atmosphere, leading us into the era of the Great Bombardment. Following the titanic impact that birthed our moon, the early solar system remained a tumultuous place. For hundreds of millions of years, Earth, along with its planetary siblings, was subjected to a relentless rain of asteroids and comets, a period known as the Great Bombardment. This was not an infrequent occurrence, but a constant, pervasive threat. Imagine the night sky, not filled with distant stars, but with the searing trails of incoming projectiles. These impacts were not mere punctuation marks in Earth's history. They were formative events, shaping the planet's surface and significantly influencing its early atmosphere and the potential for life. The energy released by these collisions was immense, each impact capable of causing widespread devastation. Craters some hundreds of kilometers across would have scarred the surface, evidence of a world under constant siege. These impacts melted rock, spewed debris high into the atmosphere, and contributed to the planet's internal heat. But this bombardment was not just about destruction. It also delivered crucial ingredients to our nascent planet. Comets, icy bodies from the outer solar system, are thought to have brought significant quantities of water to Earth. Asteroids, too, carried water and organic molecules, the very building blocks of life. The ceaseless impacts would have created a highly dynamic environment. Volcanic activity, already prevalent due to Earth's internal heat, would have been exacerbated by the impacts. The atmosphere, thick with vapor and volcanic gases, would have been a chaotic soup of steam and impact ejecta. This period, stretching from about 4.1 to 3.8 billion years ago, is a time shrouded in mystery, as direct geological evidence is scarce. However, the lunar record, less disturbed by erosion and tectonic activity, shows a dramatic increase in impact cratering during this time, leading scientists to infer that Earth experienced a similar onslaught. The constant barrage would have made the emergence of stable, complex life incredibly challenging. Any delicate beginnings would have been wiped out by the next significant impact. Yet life, in its most primitive forms, may have found refuge in the deep oceans or hydrothermal vents, shielded from the worst of the surface chaos. The Great Bombardment, though violent and destructive, played a dual role. It punctuated Earth's early evolution with cataclysm, but it also delivered the water and organic compounds that would, against all odds, eventually give rise to life. As this era of intense bombardment began to wane, a new, and perhaps even more significant, transformation was taking place deep within the planet. The cooling of Earth was not just reducing impacts, it was initiating a process that would eventually lead to the formation of the very ground beneath our feet, ushering in the age of the Hadean Aeon. As the relentless fury of the great bombardment began to subside, Earth, still a young and volatile world, started a slow, arduous process of cooling. Deep within its molten heart, the gravitational forces had already begun to separate rock from metal, forming a nascent core. Now the surface, for the first time, had the potential to solidify, to transition from a sea of magma to a nascent crust. This was the dawn of the Hadean Aeon, a period stretching from about 4.5 to 4 billion years ago. The term Hadean itself evokes a sense of hellish conditions, and for good reason. While the intense bombardment was lessening, the planet remained incredibly hot. Continual volcanic activity spewed forth vast quantities of gases, primarily water vapor, carbon dioxide, and nitrogen. As the surface began to cool, these gases condensed. Imagine a sky choked with clouds, a perpetual storm, and as the temperature dropped further, these clouds began to release their burden. This was the onset of the Hadean Aeon's most transformative feature, the formation of the primordial ocean. Torrential rains, lasting for perhaps millions of years, poured down onto the cooling crust. These waters, initially acidic due to dissolved volcanic gases, began to pool, forming the first oceans. This was not the gentle, life-giving oceans we know today. This was a steamy, turbulent expanse, a vast, shallow sea covering much of the planet's surface. The newly formed crust was likely thin and unstable, constantly being reshaped by volcanic eruptions and the slow drift of nascent tectonic plates. The early atmosphere was still dominated by carbon dioxide, creating a powerful greenhouse effect that kept the planet warm despite the young sun being fainter than it is today. There was no free oxygen, and the conditions were utterly alien to most forms of life we are familiar with. Yet, within this harsh environment, a crucial chemical soup began to form. The interaction of water, volcanic minerals, and the energy from lightning and hydrothermal vents created a complex mixture of organic molecules. These were the raw ingredients, the building blocks, awaiting an even more opportune moment to assemble themselves into something truly extraordinary. The oceans of the Hadean were a cradle, albeit a fiercely protective one, for the very beginnings of life. They provided a stable medium, a place where chemical reactions could occur, shielded from the harshest radiations and the remaining, albeit reduced, bombardment. The formation of these primordial oceans was a monumental shift, transforming Earth from a primarily molten body into a planet with distinct surface features. It was the essential precursor for the development of more complex geological processes and, most importantly, for the emergence of life itself. But the Hadean was a preamble, a harsh but necessary stage, leading us to what many consider the true beginning of life on Earth, the era of the Archean Eon. The Hadean Eon, with its molten surface and torrential rains, eventually gave way to the Archean Eon, a period stretching from about 4 to 2.5 billion years ago. While still a harsh and alien world, the Archean represents a pivotal moment in Earth's history, the undeniable emergence and diversification of life. The cooling Earth had now established a more stable crust and vast, shallow oceans. Volcanic activity was still rampant, releasing gases that would begin to slowly alter the atmosphere. But the crucial difference was the presence of liquid water, a stable solvent, and the accumulation of organic molecules, the very ingredients for life. It is here, in the ancient oceans, that the first fragile sparks of biological activity began to flicker. Scientists believe that life originated as simple, single-celled organisms, likely prokaryotes, bacteria, and archaea. These microbes were extremophiles, thriving in the hot, chemically rich waters, near hydrothermal vents, or in shallow, sunlit pools. These early pioneers were not photosynthetic. They derived their energy from chemical reactions, a process called chemosynthesis. They were the unseen architects, quietly transforming the chemical landscape of the early Earth. Their existence, though invisible to us for so long, is etched into the very rock record, particularly in formations called stromatolites. Stromatolites are layered structures formed by the activity of cyanobacteria, a type of early photosynthetic microbe. These ancient bacteria, using sunlight, water, and carbon dioxide, began to release a byproduct that would profoundly change the planet: oxygen. Though initially released in small amounts, this oxygen was a revolutionary development, a true game changer. The Archean crust was still geologically active, with continents beginning to form and coalesce. These early landmasses were smaller and more scattered than today's continents, but they represented the first solid ground. The oceans, however, remained the primary cradle of life. The slow accumulation of oxygen, though toxic to many early life forms, was setting the stage for a monumental transformation. It was a gradual shift, a slow poisoning of the old world by a new one. The impact of these tiny, photosynthetic microbes was immeasurable, a testament to the persistent, transformative power of life. The Archean Eon is a period of profound biological innovation, a time when the most fundamental processes of life were established, and the very composition of Earth's atmosphere began its slow, irreversible change. The implications of this oxygen production were so vast, so impactful, that it would usher in an era of unprecedented planetary transformation, a dramatic shift known as the Great Oxygenation Event. For billions of years, Earth's atmosphere was largely devoid of free oxygen. The life that emerged in the Archean Aeon, the pioneering cyanobacteria, began to change this, releasing oxygen as a waste product of photosynthesis. However, it was not until the Paleoproterozoic era, approximately 2.4 to 1.6 billion years ago, that this gradual process culminated in a radical, planet-altering event known as the Great Oxygenation Event, or GOE. This was not a gentle transition. It was a revolution, a mass extinction event for much of the anaerobic life that had dominated Earth for eons. Oxygen, in its pure form, is a highly reactive gas, toxic to organisms that had evolved in its absence. The accumulating oxygen began to react with dissolved iron in the oceans, forming vast deposits of banded iron formations, clear evidence of this momentous chemical shift. As the dissolved iron was oxidized, the oxygen began to escape into the atmosphere. This was a slow but relentless process, fundamentally altering the planet's air. The implications were staggering. For the microbes that could tolerate oxygen, it offered new metabolic pathways, a far more efficient way to generate energy. This event was a testament to the profound power of biological innovation. The humble cyanobacteria, through billions of years of photosynthesis, had inadvertently created a world hostile to its ancestors, but fertile for its descendants. The accumulating oxygen drove further evolutionary change, paving the way for more complex life forms. The GOE also had significant implications for Earth's climate. Oxygen reacted with methane, a potent greenhouse gas, reducing its concentration in the atmosphere. This may have contributed to a series of global glaciations, known as snowball Earth events, where much of the planet was covered in ice. These dramatic climate shifts, while challenging, also spurred further adaptation and diversification of life. The Great Oxygenation Event was a profound turning point. It marked the end of an oxygen-poor world and the beginning of one where oxygen would become essential for the evolution of complex, multicellular life. It was a demonstration of how biology could fundamentally reshape planetary chemistry and climate, setting the stage for the explosion of life that would follow. Yet the surface of the Earth was still a dynamic place, with continents drifting and colliding, leading us to the era of the supercontinent cycles. The seemingly solid ground beneath our feet is anything but static. For billions of years, Earth's outer shell, the lithosphere, has been broken into immense plates that slowly drift, collide, and separate, driven by the immense heat from the planet's interior. This perpetual motion gives rise to the grand phenomenon of supercontinent cycles, a rhythmic assembly and breakup of continental landmasses that has profoundly shaped Earth's geology and climate. These cycles, operating over hundreds of millions of years, involve the gradual movement of continents across the globe. They begin with the rifting of existing landmasses, the pulling apart of continental crust, leading to the formation of new ocean basins and volcanic activity. Over vast stretches of time, these smaller continents drift towards each other, eventually colliding and fusing to form a single, massive supercontinent. The most well-known of these ancient supercontinents is Pangaea, which existed during the late Paleozoic and early Mesozoic eras. But long before Pangaea, there were other such colossal landmasses, like Rodinia and Columbia, each a testament to the restless nature of our planet. The formation and breakup of supercontinents have profound implications for global climate and sea levels. When continents converge, they create massive mountain ranges, altering atmospheric circulation and contributing to long-term cooling. The breakup of supercontinents, conversely, can lead to increased volcanic activity, releasing greenhouse gases and warming the planet. These cycles also play a critical role in the evolution of life. The formation of a supercontinent can create vast inland deserts and arid regions, isolating populations and driving speciation. Conversely, the breakup of landmasses can create new marine environments, opening up ecological niches. The geological forces that drive these cycles are immense. A slow-motion ballet of lithospheric plates, the heat from Earth's mantle acts as the engine, creating convection currents that drag the plates along. This process is not only responsible for the shape of our continents, but also for the distribution of resources, the formation of mineral deposits, and the occurrence of earthquakes and volcanic eruptions. Understanding these supercontinent cycles is key to deciphering Earth's past, as the distribution of ancient rocks and fossils across continents provides compelling evidence for their former existence. These cycles are a reminder of the immense geological forces still at play, shaping our planet on timescales that dwarf human comprehension. As we witness the slow dance of continents, we begin to grasp the sheer dynamism of our planet. But this ceaseless movement and transformation also raise profound questions about the long-term habitability of Earth. Are there limits to this geological ballet? And what happens when the very engines of change begin to slow? This leads us to explore the enigmatic concept of the long, slow fade, the engines of Earth's dynamism, the convective currents within its mantle that drive plate tectonics and fuel volcanic activity, are not eternal. While the planet remains geologically active today, the long-term prognosis suggests a gradual decline in this internal heat, a phenomenon often referred to as the long, slow fade. The Earth's internal heat originates from two primary sources: the residual heat from its formation and the radioactive decay of unstable isotopes within its core and mantle. Over billions of years, this primordial heat has been slowly radiating away into space. The rate of radioactive decay also gradually decreases as the available isotopes are consumed. As this internal heat diminishes, the vigor of mantle convection will inevitably lessen. This will lead to a slowdown in plate tectonic activity. Continents will drift more sluggishly. Volcanic arcs will become less active, and the rate at which new oceanic crust is generated will decrease. The consequences of this fade are profound. Plate tectonics, the driving force behind mountain building, volcanic arcs, and the recycling of Earth's crust, is directly linked to the planet's habitability. It plays a crucial role in regulating Earth's climate over geological timescales. By influencing the carbon cycle and the distribution of continents, as plate tectonics slows and eventually wanes, the mechanisms that regulate Earth's climate will weaken. The recycling of carbon dioxide, a key greenhouse gas, will become less efficient. This could lead to a gradual increase in atmospheric CO2 over very long timescales, potentially resulting in a runaway greenhouse effect, similar to what is observed on Venus. Furthermore, the formation of new landmasses and the creation of diverse geological environments, which have been crucial for the evolution of life, will also diminish. The dynamic geological processes that have fostered biodiversity may eventually cease, leading to a more static and potentially less habitable planet. While this fade is occurring on timescales of billions of years, it is a fundamental aspect of planetary evolution. It suggests that Earth, like all planets, has a finite period of intense geological activity. Understanding this slow decline is not a cause for immediate alarm, but a profound insight into the long-term destiny of our planet and the systems that sustain life. The concept of the long, slow fade reminds us of the transient nature of even the most seemingly permanent geological processes. It prompts us to consider what happens when the very forces that shaped our planet begin to recede, and how life might adapt or ultimately fail in a decelerating world. This contemplation naturally leads us to ponder the ultimate fate of the sun itself and how its own long journey influences our planet's distant future. Our planet is inextricably linked to its star, the sun. The fiery arc of its existence, from its birth to its inevitable demise, dictates the energy budget and the ultimate habitability of Earth. While we have focused on Earth's internal processes, the sun's own stellar destiny casts a long shadow over our planet's future. Even on timescales of billions of years, our sun is currently a main sequence star, a stable fusion reactor converting hydrogen into helium in its core. This process releases an immense amount of energy, providing the light and heat that sustain life on Earth. However, this stable phase is not eternal. The sun, like all stars, has a finite lifespan, governed by the amount of hydrogen fuel in its core. In about 5 billion years, the sun will exhaust the hydrogen in its core and begin to swell, entering its red giant phase. Its outer layers will expand dramatically, engulfing the inner planets, including Mercury and Venus, and potentially Earth itself. The surface temperature of Earth, even if not engulfed, would become scorching, rendering it completely uninhabitable. After the red giant phase, the sun will shed its outer layers, forming a beautiful planetary nebula, and its core will collapse to become a white dwarf, a dense, hot remnant that will slowly cool over trillions of years. This white dwarf will emit very little heat, leaving planets in its vicinity in a frigid, lifeless state, while the engulfment of Earth by a red giant sun is a distant prospect. The sun's evolution has more immediate implications. Over billions of years, the sun will gradually increase in luminosity. Even a small increase in its energy output will have significant consequences for Earth's climate. As the sun brightens, the amount of solar radiation reaching Earth will increase, leading to a gradual warming of the planet. This increasing solar luminosity will eventually overcome the cooling effects of geological processes and the carbon cycle. Even before the red giant phase, the oceans will likely boil away, and the atmosphere will be stripped away by the intense solar wind, rendering Earth a barren, desiccated world. The sun's fiery arc is a cosmic clock, ticking down the time available for life on Earth. It is a stark reminder that our planet's habitability is not a permanent state, but a consequence of a delicate balance between internal processes and external stellar influences. Contemplating the sun's ultimate fate forces us to confront the ephemeral nature of life itself and the vastness of cosmic timescales. It opens our minds to the possibility that life may not be unique to Earth, and that other worlds far beyond our solar system may currently exist in more favorable stages of their own planetary and stellar evolutions. This wonder about other worlds brings us to the contemplation of exoplanets, the vast unknown beyond our solar system. As we gaze at the night sky, a tapestry of distant stars, we are struck by the immensity of the cosmos. For millennia, humanity has pondered whether we are alone, whether other worlds, perhaps teeming with life, exist among these celestial lights. The field of exoplanet research has transformed this philosophical inquiry into a scientific pursuit, revealing a universe far richer and more complex than we could have imagined. Exoplanets are planets that orbit stars other than our sun. For centuries, their existence was a matter of speculation, but in the last few decades, with the advent of powerful telescopes and sophisticated detection methods, we have confirmed the existence of thousands of these distant worlds. The sheer number of confirmed exoplanets suggests that planets are not a rarity, but a common byproduct of stellar formation. The methods used to detect exoplanets are ingenious. The transit method, for example, observes the slight dimming of a star's light as an exoplanet passes in front of it. The radial velocity method detects the tiny wobble of a star caused by the gravitational pull of orbiting planets. Each detection is a triumph of human curiosity and technological innovation. What we are discovering is an astonishing diversity of exoplanets. We have found gas giants larger than Jupiter, rocky worlds similar in size to Earth, and super-Earths, planets larger than our own but smaller than Neptune. Some orbit their stars closely, experiencing intense heat, while others are frigid worlds in the distant reaches of their solar systems. Crucially, astronomers are identifying exoplanets within the habitable zones of their stars. This is the region around a star where conditions might be right for liquid water to exist on a planet's surface, a key ingredient for life as we know it. The discovery of these potentially habitable worlds ignites our imagination and fuels the quest to understand if life, in any form, exists beyond Earth. The study of exoplanets is not just about cataloging new worlds. It is about understanding the processes of planetary formation and the conditions that allow for the emergence and sustenance of life. It is a quest to answer fundamental questions about our place in the universe and the prevalence of life. As we continue to explore these distant realms, we are confronted with the humbling realization of the vastness of the cosmos and the sheer number of potential abodes for life. And as our understanding of exoplanets grows, our perspective on our own planet, Earth, also deepens. We are reminded of its preciousness and the unique confluence of factors that have allowed us to thrive. This contemplation naturally leads us to reflect on Earth's own deep past and the subtle signs that hint at even earlier, perhaps forgotten, epochs of life, leading us to the mystery of shadow biospheres. Our understanding of life on Earth is built upon the DNA helix, the familiar code that governs all known organisms. But what if this code, this universal blueprint, is not the only way life can be assembled? What if, hidden in the deep recesses of our planet, or in environments we have yet to fully explore, there exist forms of life with entirely different biochemical foundations, what scientists call shadow biospheres? The concept of a shadow biosphere refers to hypothetical ecosystems composed of organisms that do not share our common ancestry or our fundamental biochemistry. They might utilize different genetic material, such as XNA nucleic acids, instead of DNA or RNA, or employ alternative amino acids in their proteins. They could thrive in extreme environments where our known life forms struggle, or perhaps exist in subtle, overlooked niches right alongside us. This idea arises from the principle of chemical contingency. Life arose on Earth under specific conditions, and the specific chemical pathways and molecules that proved successful became dominant. However, it is conceivable that other chemical pathways, given different evolutionary pressures or environmental conditions, could have also led to life. Imagine microbes that utilize arsenic instead of phosphorus in their molecular structures, or organisms that incorporate entirely different sets of amino acids into their proteins, leading to proteins with alien three-dimensional shapes. These would be life forms, undeniably, but life forms so distinct from our own that we might not even recognize them as such. The search for shadow biospheres is a frontier of astrobiology and microbiology. Scientists are looking for unusual metabolic signatures in extreme environments, such as deep underground caves, anoxic ocean sediments, or even within rocks, places where life might persist in isolation from the dominant biosphere. The implications of discovering a shadow biosphere would be profound. It would demonstrate that life is not a singular event, but a potentially diverse phenomenon with multiple possible solutions to the challenges of existence. It would revolutionize our understanding of biology and profoundly impact our search for life beyond Earth, as we would need to broaden our definition of what life can be. This idea challenges our very definition of life and hints at the possibility that life may have arisen more than once on Earth, or that it exists in forms so alien we have not yet learned to see it. It opens up a universe of possibilities, reminding us that the story of life on Earth may be far from complete, and that even our own planet may hold secrets we are only just beginning to uncover. These enduring mysteries, hidden within Earth's own history, point towards the immense scope of what we do not yet know about our planet, a thought that naturally leads us to the ultimate contemplation of the end of all things. Our journey through the deep history of Earth and the cosmos has been one of awe and wonder, of cataclysm and creation. We have traced the fiery genesis of our planet, the slow accumulation of water, the improbable spark of life, and the grand cycles of continents that have shaped its surface. We have gazed at distant stars and imagined other worlds, and we have pondered the possibility of life in forms unseen. Now, as we stand at the precipice of these vast contemplations, we must confront the ultimate question, the end of all things, not the end of a single epoch, or even the end of our species, but the eventual, inevitable conclusion of Earth and its cosmic neighborhood. The forces that have shaped our planet are not permanent. The sun, our life-giving star, will eventually exhaust its fuel, expanding into a red giant and likely engulfing Earth. This stellar death, though billions of years away, is a cosmic certainty, even without the sun's demise. Earth's own internal engine, the heat that drives plate tectonics and volcanic activity, is slowly fading. The long, slow fade will eventually lead to a geologically dormant planet, a world stripped of its dynamic processes and its capacity to support complex life. The universe itself is not eternal, while the current expansion of the cosmos may continue for eons. Theories suggest various ultimate fates, from a big freeze, where the universe cools to absolute zero, to a big crunch, where gravity eventually pulls everything back together. Regardless of the specific scenario, the vastness of time suggests an end to the processes that give rise to stars, planets, and life. This contemplation of the end is not one of despair, but of profound perspective. It highlights the preciousness of our present moment, the ephemeral beauty of life on this vibrant planet. It underscores the extraordinary nature of Earth's existence, a fleeting but magnificent anomaly in the grand cosmic narrative. Our journey has been a testament to the enduring power of scientific inquiry, to our innate drive to understand our origins and our place in the universe. Each layer of rock, each fossil, each distant star is a fragment of this grand story, a piece of a puzzle that continues to unfold. The whispers of the strata, the echoes from the primordial forge, the silent testament of deep time, all converge on this single, undeniable truth. Existence in all its forms is a continuous process of change, of becoming, and ultimately of fading. And in understanding this grand arc, we gain a deeper appreciation for the brief, brilliant flicker of life that illuminates our corner of the cosmos. Make sure to subscribe for more videos and hit that notification bell so you never miss a new video. We'll see you in the next one.